So last time before the midterm, I was talking about dynamic programming. And the topic, the particular problem we were looking at was interval scheduling, weighted interval scheduling. So we have intervals as before, and now each interval has some value. And again, we have to pick intervals that are pairwise non-overlapping. So we're not permitted two intervals that overlap. And we want to find a set of non-overlapping intervals that maximizes the total value of the intervals you take. Well, in this little example, it's pretty clear. You definitely want to take the 26, and the 13 doesn't overlap it, so that's good. And that's it. That's 39 is the value of the optimal solution that you can get. And the dynamic programming, or the solution we've looked at so far, was a recursive solution, where, again, as in the case of just maximizing the number of intervals, the first thing we do is we sort the intervals by their finish time. So this one now will be interval 1 because it has the first finish time, right? And then this is interval 2. This one is interval 2 because it has the second finish time. Third finish time is here. Fourth is here, right? Fifth is here. And the sixth is here. So that's the ordering of the intervals. 1, 2, 3, 4. Oops. Oh, yeah, 5. That's the interval number. This is the weight. 5, and then 6. Okay? So the intervals are, again, ordered by finish time, and they have a weight to them. And then we defined opt of j is equal to the value of the optimal selection among intervals 1 through j. So not that you're going to take all the intervals 1 through j, it's just those are the ones you have to select from. And there's an optimal selection of intervals, pairwise non-overlapping intervals, to maximize the weight of what you get, just if you restrict attention to intervals 1 through j. And then what we want, of course, is opt n, where n is the number of intervals. And that gives you the value of the optimal solution. It doesn't tell you the selection of the intervals itself. We'll get to that today as well. But right now, we're still talking about how we're going to compute opt-n. And then what we did is we observed the recursion. We could express opt-j is equal to the max of opt-j minus 1, or vj plus opt-pj. Okay? Well, what was vj? Vj is the value you get from interval j. So here's j with value. So this is v1 is 5, v2 is 13, etc. in this example. So the v is the value you get. Now what was pj? Pj for an interval j is the interval that's closest to j, but non-overlapping. Its finish time is the closest to the starting time of j, but it doesn't overlap j. Okay, so pj, again, pj is an interval. It has to be less than j, and the start time of the finish time, oh, this doesn't say it doesn't overlap it. pj, okay, let's go back. The finish time of pj is less than the start time of j. So that says it's before j, but it doesn't overlap it. So the finish time is to the left, it doesn't overlap it. And pj is the max interval index with that property. So I have a feeling I said this nicer last time in some different way, but this is certainly correct. The finish time of pj is an interval, so it's an index or an index to an interval, but you can see here it's indexed on j. It has to be less than the start time of interval j, and pj is the max index with that property. So if we're looking at j, here pj is, if this is j, pj is equal to 2, right? In this little example. Interval 2 finishes before j starts, and I think it's the closest interval to j that has that property. So the largest index that has that property. Okay, so the recursion is saying the best thing you can do when you're looking at intervals 1 through j comes from two possibilities. Either you don't take interval j, in which case the best thing you can do is what you can do with intervals 1 through j minus 1. That's what this is saying. Or you are going to take j, in which case you get its value, but then you can't take anything that overlaps it. You're not permitted to take anything that overlaps it on its left side. And so the best you can do with the intervals that remain, that are available, permitted, is opt of pj, the intervals 1 through pj. Okay? So any questions on this? This is really the critical insight. And when you do dynamic programming, we do recursive kinds of, finding a recursive solution to various problems, coming up with this kind of recursion, this kind of analysis, is really the key step. The other kinds of things are somewhat mechanical after that. But deciding how you're going to look at the problem recursively and what the recursion is the key conceptual and creative thing that you do. Okay, so any questions on this? Comments? It's just totally quiet class. Or it's all right. I know what it is. There's no class in the other room. There's usually a chattering that goes on from the other room. I mean, I'm hearing them right on the board there, but for some reason they're not there today, so it's really quiet up here. Okay, so that's the recursion. And then we said that you could take this recursion and turn it into a recursive program. I wrote it up, some pseudocode last time, which I'm not going to write up. But then if we look at the execution of this as a recursive program, the first thing you'll call is opt of n. That's what you want. You want to know what's the value of the best solution in intervals 1 through n, all of the intervals. Okay? And opt of n, based on this recursion, is going to call opt of n minus 1. That's this possibility. Or it's going to look at vj, well, it's going to, if I'm just looking at the calls, the recursive calls, because of this part of the recursion, it's going to call opt of pj. Okay? And then each of these recursive calls call, and finally we get down to the base case, which I didn't write up, but opt of 0 is 0, or let's just leave it at that. Opt of 0 is 0. I'm not going to write that here. Opt of 0 is equal to 0. Okay, if you have nothing to schedule, you have no intervals at all, then the best thing you can do is 0. So this is what the recursion, the tree of recursive calls would look like if you just programmed this up as a recursive program. And I suggested to people that they could actually do this. And because you'd have to try to figure out how you input the intervals and so on. So there's some mechanics in writing that program. But the key thing here is that there's a lot of redundancy in this. The same recursive problem could be called over and over and over again. And we actually saw an example of that where the number of recursive calls on n intervals grew like the Fibonacci number. The Fibonacci number on n is exponential in n. So the number of calls grows exponentially. Very inefficient. Okay, everybody remember how that went or why that happened? So top-down recursion is inefficient. And it's because of repeated calls to the same subproblems. The same subproblem. Okay? But in this problem, this particular problem, the number of distinct subproblems, the number of different subproblems that exist, is bounded by what? What? N minus 1? Yeah. Is that what you said? Okay, good. N minus 1. Yeah, the subproblem is parameterized by what's in here. Okay, this is some index. It's an index between 1 and n. And or from the set of integers 1 through n. So there are only n minus 1, or actually once you get down to, okay, now that I've set the base case of opt 0 equals 0, now it's actually n. All right. But at any rate, there are only n different distinct possible subcalls that are made, and yet this tree of recursive calls grows exponentially, which is, again, another way of saying that the same subcalls are getting made over and over again. So there's a general trick or idea that is used to make any recursive, the execution of a recursive program more efficient, except it adds a little bit of overhead. So if the overhead doesn't defeat, so as long as the overhead doesn't defeat the advantage of this next idea, in all recursive programs you should incorporate it, because it will make it'll make the recursive program more efficient, even if you don't have an analysis that says how efficient it becomes. It may just make it efficient in practice, and not necessarily in a worst-case sense. Although in this example, it will make it efficient in a worst-case sense. And the idea is this awful word, memoization. Okay? And there are two components to that. One is you make the calls, make the recursive calls in a depth-first manner. And that's almost automatic anyway in most implementations, in most ways that you're going to write the program. But if you think of this as the tree of all the recursive calls that are going to be made, you could imagine some implementation that's not depth first. You call this first, then you call that, and then you call that, and then you call this. And you could bounce all over the place in the tree of recursive calls as long as the parent had already been called for what your next recursive call is. But if you do a depth first, then you'll call this, and then this one, and then the one that's below it, and the one that's below it, and so on. And you'll finally get down to a base case of opt of 0, and then you'll start percolating up, and so on. And we looked at this last time in detail. So there's nothing wrong with implementing this as a depth-first traversal. It's certainly no less efficient than any other implementation. So we do that. You'll see in a minute why we want to do that. And then the next, I guess there are three pieces to this. The next thing is that when opt of j is computed, okay, store its value in a table. Well, and what's a good name for this table? You might call it opt. Now, for some reason, the book, in this exposition, everything is called opt until around this point, and then it all of a sudden becomes M. So when you read the book, you note that change, but there's no particular reason for it. I don't know why they did that. Okay, now, so what does that mean? Here we do the depth first traversal. We get down to opt 0. Okay, then we go over here, and whatever has to be done. And finally, we come back up here, and once both sides have been explored, the value here of this, whatever this call was, opt of 2 or whatever, opt of 1, that's done. We know what its value is at this point. We've done all the recursive calls below it, and we've come back up, so we know its value. And that's what I mean that when opt j is finally computed, you store its value. So as you percolate back up in the depth first expansion and exploration of this tree, you're coming back up, and here's j, and you've looked at both sides, and you come back up to j, and now you know its actual value, and you put it in the table. Okay? 3, before making any recursive call to opt, I'll just use another variable just so we don't confuse things. Let's say to opt k, okay, check the table to see if opt k is already known. Okay? So, and this is getting very cluttered here. Let me. So you're doing this in a depth first manner, and there you finally know that value, and you come back up here and do this, whatever, you finally know that value, and so on. And let's say here is opt of n minus 1, finally gets computed, and you know its value. So it's stored. Okay, so, oh, actually, n minus 1, that's probably a little too tight. Let's say, this is n minus 3 or something. Okay, so over here, you get down to a place where you're about to call opt n minus 3 in the top-down recursion. You're about to call opt n minus 3, but you don't. Instead, you look up in the table to see if that's already known, and it is. So what's the point of doing all the stuff that's beneath here? Okay, there's no point at all because you already know its value. So you can cut that out, and you don't need to do all that recursive calls and computation. So before making any recursive call, check to see whether that's already known, and if so, just use it. You don't have to issue additional recursive calls. You just use it. Otherwise, you make the recursive call as before. Opt k. Okay? So what are you saving here when you look up opt n minus 3, for example, and you find that it's already known? What are you saving in computation? It's not just you're saving one little effort because you already know it. You're saving enormous because this entire subtree of recursive calls and all the work that would be done in there, that's completely gone now. Okay? So it seems like a good idea, unless the overhead of putting things in a table and looking things up is more than the advantage of doing this, but in all but the most very efficient kinds of maybe tail recursion or some situations like that, this idea of memoization will definitely be of value. Okay, but let's try to analyze how much of value. Again, it seems like a good idea, and if you program this recursively, you could add in this heuristic, this additional idea very easily, and you would see very dramatically in these kinds of problems how effective this was. So that might be a good thing for people to try to do. Let's do an analysis of what's the worst case running time of this top-down recursion when you use memoization. Anybody have a suggestion on how to do that? Actually, the book has an analysis, which I don't like. I don't know why they... well, it's probably okay, but it wasn't the way I wanted it. So, the worst case running time of the memoized algorithm is theta n. Okay? So we went from something without the memoization, something which was exponential in n, something huge in n, down to something which is about as small in n as you can get. What's so funny? Okay. Something's funny. All right. So you get down to as small as possible. The order n is really just what you would get from touching all the data. Every piece of the data has got to be examined. Okay. How do we prove this? Well, the first thing to observe in the memoized version, how many recursive calls does the memoized version actually make? N minus 1 or n. I mean, it only makes a particular type of recursive call once. Okay? Every time, and that's because of the depth first nature and the fact that these intervals are getting smaller. Okay? The parameter here always gets smaller as you go down. So this is n, this is something less than n, and so on. It gets smaller as you're going down here. Okay? So you're never having the same call twice in a depth first path. And that means that you're going to get the value of a particular recursive call in this depth first approach before you would ever call it again. The next call of this opt, like opt n minus 1, will be somewhere in another part of the tree, not below where this opt call is made. So that's the first observation, is that opt j for any j is made only once. Or the call to opt j, the recursive call, where you're actually going to go in and do the recursion, do the computation. The call to opt j for any j is only made only once. And as I said, that's a property of the fact that you're doing the depth first traversal. If we didn't do depth first, we couldn't make that claim. If you came over here and you made this recursive call, but then you stopped and you started doing this recursive call and so on, you could easily have multiple calls of the same opt subproblem. But when you're doing it top down, when you're doing it depth first, then that won't happen. And the fact that this is recursion, where you're calling a subproblem for any op j, you're calling a subproblem of it, then you're never going to call the same subproblem in a subtree that's below that subproblem. Okay, and those add up to this op j for any j is made only once. So only, I'll call it n, recursive calls. Okay, now if you look at the actual tree of executions with the memoized idea, you get not only recursive calls. Let's say this is a recursive call and this is a recursive call. These are recursive calls. Here we're not doing recursion because we're down to the base case. And here we have this where we would call, let's say, opt-n minus 3, except we look up and we find that we already know it. So that's not a recursive call, but yet it's part of the algorithm. It takes some work. Okay? So we have to account for that too. So when you look at the whole tree of what the algorithm looks at, of course this part is gone, and that was the whole advantage of doing this, but there was some work involved when it was thinking about maybe calling this opt. It was the work of looking into the table and deciding that wasn't true and then it backs up and so on. Okay, but so how do we handle that? Well, the key point, that board is full, so I'll come over here. So we have in the tree some nodes where recursive calls are made. And then we have some places where the algorithm was thinking about maybe making a recursive call but decided not to because that value was already known. Okay? And maybe here we have two of them. Okay? So what we just argued is that you have at most n of the nodes where recursive calls are made. At most n nodes where recursive calls are made. Now, if you have a node that has no recursive call, where the algorithm decided, no, I'm not going to do that recursive call because I already have that value, how many children does it have? How many recursive calls are there? How many calls are there below a node that has no recursive calls? 0. Okay? This is a leaf. No children. Okay? No children, no calls. And its children have no children, right? Well, it doesn't have any children, so that's vacuously true. Which, by the way, reminds me that having children is a hereditary property. If your parents don't have any children, chances are you won't have any either. Okay. At any rate, these guys who make no calls, that's a dead end. Okay? Now, a node that does have a recursive call, how many children does it have at most that don't make recursive calls? 4? No. Well, possibly 2. So oh, I'm sorry, you're right. I'm saying it's making a recursive call. Well, no. It makes a recursive call to something down here, but then this one realizes it doesn't have to make a recursive call. And this one makes a recursive call to this one and realizes it doesn't have to make a recursive call. So and what I'm saying is that a node that makes a recursive call, it either has 2 children that make recursive calls, or it has 1 child that makes a recursive call, or it has, and so conversely it has 1 child that doesn't, or it has 2 children that don't. Okay? So a node that makes a recursive call has at most 2 children who don't make recursive calls. Okay? So in this tree, where we're seeing the behavior of this algorithm, we have n nodes that make recursive calls, and attached to some of those nodes are nodes that don't make recursive calls. But if you're a node that doesn't make a recursive call, you're a leaf. You're a dead end. There's nothing below you. So I can ask, in this tree that describes what this algorithm is doing with memoization, how many nodes are there at most? Yeah.
2 or 3n.
Okay. Yeah, 3n is certainly, it's at most 3n, because we know that there are at most n nodes that make recursive calls, and we know that there's at most 2 nodes hanging off of such a node that don't make a recursive call. So that total is 3n. Now, it may feel like that's a little bit too big, and you're probably right, that if you looked a little more carefully, then because in order for the tree to actually get going somewhere, a node that makes a recursive call has to have a child that makes a recursive call. And so when you factor that in, my guess is that you could actually prove a bound of 2n. But whether it's 2n or 3n, it's still theta of n. Okay? So just the fact that from a node that makes a recursive call, you can have at most 2 children of it that do not, means that the total number of nodes is at most 3n. So total number of nodes is less than or equal to 3n, which is theta of n. Okay, so that's the end of the analysis of this algorithm memoization, or the proof of this theorem that we have over here. So an amazing speed up from exponential time, where you'd be waiting a long time for any but a small problem, to where it's linear in the input size. Okay, I don't know of any other algorithmic idea, or this is an algorithmic idea, not just a programming idea, that has such a dramatic impact in speeding up of an algorithm or class of algorithms as this memoization idea. Okay, now you can actually take this one step further and get to what's called dynamic programming. So when we look at this recursion, we were thinking about implementing it top-down and then seeing how to speed that up through memoization. And then I think it's useful to do that because it's a general idea. And in this particular case, we were able to prove a bound on how much time that would take. But in problems where you can't prove a bound because the problem isn't structured enough, you don't have enough insight into what's going on, it's still a good idea. And so that's why I wanted to teach it to you. But in structured problems of this, like this is, you can actually go one step further and make it even more efficient and simpler to implement, which is, instead of computing these values of ops top down, it's more efficient to compute them bottom up. So dynamic programming in this viewpoint is recursive programming implemented bottom up instead of top down. Instead of top down. Well, by top down, I mean that the first thing you call in the program was opt of n, and then it makes recursive calls and finally hits the base case and then starts bubbling back up. But bottom up means you can compute the base case immediately and then start computing the values of opt for bigger parameters. So here's the DP version of this. Opt of 0 is equal to 0, so we can just compute that immediately, put it in a table called opt. And then sorry. Yeah. For j equals 1 to n, opt of j, well, okay, it's just this thing. I'll write it again. No, I won't. Okay, it's just this over here. And the point is that opt of 0 equals 0. We're ready to compute that. We can compute that at the very beginning. Then you want to compute opt of 1. Well, if you look at the recursion over here, what do you need to be able to compute opt of 1? According to the recursion, you need opt of 0. Now j is equal to 1, so 1 minus 1 is 0. You need opt of 0, and you have it. And you need v of 1, which that's part of the input to the problem, so you have that. And then you need opt of pj, so you have to compute what pj is, but that's something you can do also, left to right. For every j, you know what pj was. So in general, you can do this from j equals 1 to n. If you get up to 26, j is equal to 26, and you want to compute opt of 27, you need opt of 26, but you just computed it, so you have that available. And you need vj, which of course you have as part of the input, v of 26, and you need opt of p of 26. Well, what is p of 26? We don't know, but it's less than or equal to 26. It's less than 26, right? So we definitely have that available too. We can figure out what p of 26 is. That's just you do that when you're sorting the input initially. And at the point in which you're trying to compute opt of 26, you already know opt of p of 26 because p of 26 is less than 26, right? In general, p of j is less than j. So you can just do this iteratively. We didn't need this top-down recursive stuff and then the memoization idea to make it efficient. We could just do it like this, in this simple iterative approach. Now it's clear that this takes theta n. Well, first of all, it should be clear this is right. Okay, why is it right? Because it's just following the recursion. If the recursion is right, then the program is going to be right. It's going to compute opt of j properly for every j. And this takes theta n time. Okay, because we have n iterations in the loop, and in each one, what are you actually doing? You're doing one lookup, that's constant time, another lookup, that's 2, a third lookup if you want to say you're getting vj, you're adding them together, you're comparing them. It's a constant number of operations. So every opt j just takes a constant number of operations, and this loop goes through n times with a constant number of operations each time. So theta n time. So this was a lot easier than this top-down recursion. And it's easier because this problem has this nice structure where we see exactly what's going on in the recursion. And, well, you can build it up in this iterative way, and it's efficient to do so. Because the book actually has some more general discussion of when you can go from the memoization idea to a bottom-up dynamic programming idea. Okay, let me ask this. How does this, I said this was actually more efficient than the top-down method with memoization. They both have the same worst-case time, theta of n. But this is more efficient. It's certainly simpler. If you had to program it, it's very simple to program this as opposed to doing your top-down business and the memoization and so on. But why is this actually faster? What is the actual speed advantage of this in comparison to the top-down approach? Well, conceptually, how do the two relate to each other? Yeah.
No function calls, so you don't have to stack.
You have no function calls. You don't have to stack. That's true, and that's really that is the core of what's the efficiency. But there's another way of kind of seeing. Yeah.
It's essentially moving along just a single path through the tree, basically like the left-hand side where you're just going to the next one, and the like one less off value, and moving up through the tree like that.
Well, I couldn't hear what you said, but but you must be right, because your hand motions were about right. The point is that when you do the top-down, when you're doing the top-down, even with memoization, you're doing these calls and stacking the calls, and finally you're getting down to some place where you have opt of 0, and you know its value, and then you're popping back up. But the point is that the upward traversal is essentially what's happening here in this iterative approach. So the top-down part of building this tree was just getting ready to where you can start doing the iterative thing going back up. And it was just kind of wasted. You're spinning your wheels building this whole big tree edifice to the point where you can start doing the actual computation. And this just eliminates all of that. And that's another conceptual view of why that's more efficient. But the fact that you're not making the calls and the stacking, that's the same thing essentially. Here it's just a more kind of visual view of that. Okay, so this is dynamic programming, at least for computing the value, computing opt. All right, so in dynamic programming, I usually think of it as having several components. Every dynamic programming problem has several components. The first one is that you think about the problem recursively, and you come up with some recursion. So BP, one is get a recursive solution for the problem. Okay, and that's really the most important. Here we have this recursive solution. In many problems, there are different recursive ways of looking at it. Some have advantages over others. Sometimes you look at it and you can't figure out a recursive solution. There isn't always one. But when you can get a recursive solution for a problem, that's your first step. Then you consider a top-down memoized implementation. Third is you ignore step 2. And once you get good at this, you can just skip this. Okay. Skip 2 and 3. And then you go to 4 is you find a bottom-up iterative implementation to compute the value, to compute the numbers, the values. And then 5 is called traceback, and that's what I'm going to, I don't think you can see this on the board here, but traceback, that's what I'm going to describe right now. So The last component of a dynamic programming solution is how you do the traceback. Traceback to find a solution, not just the value. Of the solution. Okay, so in this example we've been working with, so far we have an algorithm. We have two. We have the memoization approach and we have the dynamic programming approach that will compute opt of n, and efficiently in order n time. But that's just a number, and it's a number that's a value, and sometimes that's all you want. But in the original problem formulation, we actually wanted to find a set of intervals that are pairwise non-overlapping and that maximize the total value that you get from those intervals. Okay, so so far we haven't done that. And in dynamic programming, the traceback, which I've called step 5, is a general approach to finding the actual value, to describing the actual object that you're trying to look for, and not just its value. Okay. So the book describes that in the following way with a function called find solution. I'll just abbreviate it as find sol of j. Okay. Find solution or find sol of j, and this is saying what's, again, for problems that are restricted to intervals 1 through j, what is the actual subset of intervals that maximizes the value and that are non-overlapping. If j equals 0, do nothing, or stop. If else, if Vj plus opt of Pj is greater than or equal to opt of j minus 1, then output j, you're going to actually use interval j and call find sol of pj. Else output, no, actually just call find sol of j minus 1. Okay, I've run out of time, but that's this program, this algorithm here, will, after you've computed what the opt values, you already have those in the table, you know what those all are. This is going to sort of look backwards through the table, unwrapping the logic of the recursion to decide what's the best thing to actually do. What's the best subset of intervals to actually take? And you should be able to go through here and convince yourself that this will actually do it, and also convince yourself that the running time of this is just theta n also. It's when you're calling opt find sol, that's a recursive call, but it's not a branching in any way. Okay, it's just a trivial calling of a smaller subproblem, and basically you're just marching through the table from the end. Well, we'll go back over this next time, and next time we'll also look at another dynamic programming problem. All right, so see you Friday.